Hello everyone, this is an introduction to the real number system. Goals for today are to talk about real numbers and operations used with real numbers. So to start off with, let's talk about a definition for a mathematical system. A mathematical system consists of a finite or infinite set of symbols and at least one operation. So we have to have something to work with, usually numbers, and then we have an operation, which is something that we do with those numbers. So the real number system, here's our symbol, okay, a kind of a fancy scripted R. That stands for all of the real numbers, and that is an infinite set. So if we tried to list out all of the real numbers, we wouldn't be able to do that. We can list some of them, but there are infinitely many real numbers, so we're not able to describe it in that way. But we do know, which numbers belong to this, and we'll look at some examples. And then we have actually two operations, so we only need one to be a math system, but we have more than that. We have two. Okay, we use addition and multiplication. So these operations are ways to combine real numbers, and we say that these are binary operations, meaning that they're a symbol that's used to combine two real numbers. Right? So for example, we have 3 plus 2, and then we have rules for that symbol that tell us what to do. We know what addition means, and we know what the answer is. Right? Similarly, if we had, maybe pi, and then times, okay, we're using a bullet perhaps, pi times 4. Those are real numbers. We can combine those. We know what multiplying means. Okay, and that's 4 pi, or we could get some sort of a decimal and say what that is. Okay. So in the real number system, we have lots of different categories for numbers. So let's review these. Here's a chart from your textbook that breaks this down. All right, so real numbers can be divided into different subsets, and some of them are nested inside of other ones. All right, so a number could be in more than one of these sets. Let's start with natural numbers. Here's your symbol, a scripted N stands for natural. And those are your counting numbers, 1, 2, 3, 4, all the way up to positive infinity. Then the whole numbers, no special symbol for these, but the set of whole numbers, right, is 0, 1, 2, 3, 4, 5, etc. Right? Or we could also think of whole numbers using set terminology, okay, from the beginning of one of those previous units. Right? Whole numbers are all of the natural numbers in union with the set containing 0. So union, think of the word or. All right, if it's a whole number, then it's either natural or it's a 0. All right, and then integers. So we're continuing to kind of build out. So we have, natural numbers. Then we build out, and if you combine and add 0 into that, that becomes the set of whole numbers. And then if you add in all of the opposites of natural numbers, all the negatives, then you get the set of integers. So notice from here up, this is the set of whole numbers, and then here down, those are all of the opposites of the natural numbers, all the negatives. Okay, and then Z for integers. Okay, Z from the German word zahlen, meaning to count. All right, after integers, we have the set of rational numbers. Okay, here's your scripted Q for that. Q stands for quotient. So rational numbers are quotients, and here's a way that we could write this in symbols. All right, if it's a rational number, then it's a fraction a over b, where a and b are integers, and b is not 0. All right, so here are some examples. 4 over 9. 4 and 9 are both integers, so that is a fraction of integers. Negative 5/8, those are also both integers. 11 over 7. Then similarly, if you had something like negative 2. Okay, well, negative 2 is the same as negative 2 over 1, and that's also a rational number because that's a fraction of 2 integers. So really, any of your integers is also a rational number. These are all nested inside of the rational numbers. Okay, we can just put them all over 1 and turn them into fractions. Same thing with natural numbers. These could all go over 1 So those are all rational numbers. You may also have seen a different definition for rational numbers, for what those look like as a decimal. Okay, if you think of these in terms of decimals, then rational numbers would be any decimals that end or repeat. End or repeat. Alright, so examples would be like 0.5, because that's a fraction 1/2. Things like 0.333 repeating. As a fraction, that's 1/3. So anything that ends or repeats can be written as a fraction. Irrational numbers. Alright, if you look at decimals, it's kind of just the opposite of that. The decimals have to not end and not repeat in any sort of a pattern. So irrationals would be decimals that look like 0.12984 dot dot dot. So the dot 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 means it doesn't end, it keeps going, but then it doesn't repeat in any sort of a pattern, so that's irrational. Pi, that's a famous one. Pi is irrational. Square roots. Okay, here's some other examples here. Okay, all these square roots. And if it can't be simplified to something that's like an integer, all right, then that's irrational. Pi over 4, that is a fraction, so you might be thinking, why is that not a rational number? It's a fraction. However, pi is not an integer, so it has to be a fraction of integers to be rational. Okay, some symbols that you can use to describe the irrational numbers. Right, we use this little minus sign. We say that it's all the real numbers minus the rationals. Or we sometimes use this little kind of like a backwards division symbol, and that means all the real numbers except for the rationals. Okay, so we've got this very strong dividing line down the middle. If a number is real, it's either rational or irrational, but never both. It has to be one or the other. And then finally a definition for real numbers. Okay, real numbers would be all of the rational numbers in union with all of the irrationals. So just combine them all, put them all in one set, and that's the set of real numbers. Okay, a lot of definitions there. Make sure you have these straight. You might want to write these down or have them on hand to look back at. And then one thing we can do is classify real numbers and just see which of these categories they fall into. So here are some examples. If you'd like, maybe pause the video and try this on your own, and then restart and check your answers. Okay, so let's go through and classify each of these numbers. Alright, -8. So first of all, let's start kind of with the largest category. It's either real or not real. Right? If it's not real, then it's none of those other categories, because all of those are subsets of the real numbers. Okay, so -8, we need to decide if it's real or not, and it is real. Okay, if you can find a spot on the number line where it goes on the number line, then it's a real number. So things that are not real would be things like, let's kind of put this off to the side, not real. Okay, imaginary numbers, if you've seen I, okay, or I is the square root of -1, square roots of negatives, okay, anything that's going to give an error on your calculator. Dividing by 0, like 15 divided by 0, that's not real. Okay. Alright, so -8. -8 is real. Alright, then it's either rational or irrational, so we're going to pick one of these. Okay, and alright, so the test, look at the decimal. Does it end or repeat? Or you could also see, can it be written as a fraction of integers? Well, yeah, if we put it over 1, it's a fraction, so that's rational. Okay, fancy Q. Okay, is it an integer? All right, well, yes, it's the opposite of the natural number 8, and it is an integer. Okay. Yes, it's an integer. Is it whole? Okay, wholes are 0, 1, 2, 3, 4, etc. Right, but it's negative, so it's not whole. And then if it's not whole, it can't be natural. All natural numbers are also whole. Okay, so we stop there. So it is real, rational, and integer, but none of the others. All right, -3/4. Okay, real or not real? Yes, that's real. All right, and actually, if we do a quick check here and kind of go through the list and look at each one of these numbers, it looks like all of these are real. Okay, so we don't have any examples that are not real here. All right, is it rational? Okay, yes it is. It's a fraction. It's a fraction of integers. Okay, integer. Right, well no, it's not an integer. Right, so we stop there. If it's not an integer, then automatically it's not whole or natural or any of the other ones. Okay, and then let's look at 0. Okay, so first of all, we already decided it's real. Rational or irrational? Rational. Okay, integer? Yes, it is. Okay, go back and look through some of those sets, the listing method, the ones that were listed out, to make your decision. Okay, yes, it is whole. But no, it is not natural. Okay. All right, 0.86, and then remember with the little line over it, means that that 6 continues on and repeats forever. So this is a repeating decimal. Okay, so this one is real. Okay, this one is rational, since it's a repeating decimal, but it's not an integer, and therefore it's not whole and it's not natural. 13/5, that is real, rational, not an integer, not whole, not natural. Okay, E. This is a constant. If you type this in on a calculator and find kind of the decimal approximation, it's 2.7 something, and this continues on. All right, and if you look at the digits that are displayed on a calculator, you'll see there's no pattern to these digits. So it does continue forever, but it does not repeat. So this is an irrational number. Okay, so E is real, and it's irrational. So I'm going to use this symbol for it. You could also just write irrational. All right, and then if it's irrational, we stop. Let me flip back a slide. Okay, integers, whole, naturals, those are all inside the set of rational numbers. So if something is irrational, then it's not an integer, whole, or natural. All right, square root of 25. Be careful on this one. It's tempting to think that this is irrational since it's a square root, but square root of 25 equals 5. So you kind of need to be on the lookout for ones that simplify. It could belong to a different set than you're expecting. All right, so this is real, rational, it is an integer, it is whole, and it is natural. Okay, same thing for 6. Okay, 6 would also be real, rational, integer, whole, and natural. All right, 7.8. That's real. It is rational. If you wanted to see that this can be written as a fraction, all right, 0.8 is 8/10. So that's 7 8/10, which is 78/10, and you could reduce that if you wanted. So that can be written as a fraction of 2 integers. Right? Or you can also just use the test, check and make sure that it's a decimal that either ends or repeats, and this one ends. Okay, so it's real, rational, not an integer, so it's not whole and not natural. And then finally 8.456792851 ... Right? This is a decimal that continues forever, so this is real, but it's also irrational. All right, no pattern to those digits. Now certainly maybe there's a pattern and we're just not seeing it, but for these classifications we're just going to assume that if you don't see a pattern that's established, then it does not have a pattern in the digits that come after. All right, once we know what the real numbers are, so we've looked at some examples, we've classified them, that's our set of symbols that we're going to talk about. The other component to a system, other than a set of symbols, is an operation. So we have two of them, plus and addition and multiplication. Now you might be wondering, well, what about subtraction and division? In formal math, we don't really consider those to be operations because we don't really need them. So for example, right, if you think about the subtraction problem, 10 minus 6, right, well really, that could be thought of as 10 plus negative 6. So every subtraction problem can be rewritten as an addition problem just with a negative number. If you look at division, 12 divided by 4. All right, well really, if you remember your rules for dividing with fractions, okay, that's the same as 12 times 1/4. Okay, try it out on a calculator if you want to make sure. But we can always rewrite a division problem as multiplication by a number's reciprocal. All right, if we had 6 divided by 1/5, that's the same as 6 times 5/1, 6 times 5. Okay, things like exponents, we don't really need that either. If we had 4 to the third, exponents are just a shorter way to write multiplication. This is 4 times 4 times 4. Okay, so there's really just two main ones, addition and multiplication. Now we will talk about subtraction and division later, especially in the order of operations, but it's just nice to know that we could simplify if we needed to. Okay, order of operations. So since the system has two operations, we need a universal way to describe how to do a problem. All right, so in other words, if you had 3 times 4 plus 2, we need a universal way so that everybody knows, are you supposed to do the addition first or the multiplication first? All right, so we made this system, order of operations, and you probably at some point learned PEMDAS. All right, and I kind of like this because it's easy to remember, but it is a little misleading. All right, parentheses, exponents, multiplication, division, addition, subtraction. And it almost looks like multiplication is supposed to come before division, but that's not quite accurate. If you remember, there's kind of an extra thing that you need to remember with this, and that's that multiplication and division are really the same step, and addition and subtraction are really the same step. Right? And you work left to right in a problem. So your book expands on this and gives sort of a longer definition of the order of operations. And they say if parentheses or square brackets are present, then that's where you start. Okay, so that's still the same. Do parentheses first. Working separately above and below any fraction bar. All right, so if you see something like 11 minus 2 over 3. All right, well, you do the part above the fraction first because there's sort of an implied parentheses there that's not usually written, but that's still a parentheses. Okay, step 2, use the rules below within each set of parentheses or square brackets. Start with the innermost set and work outward. So in other words, you're always just doing parentheses first, and within parentheses, you follow order of operations as well. All right, then you do exponents, okay, then multiplications or divisions in the order in which they occur, working from left to right. So you could end up doing multiply and then divide, or maybe divide and then multiply, or maybe some combination of the two. All right, same thing with addition and subtraction. All right, there's a chance that you might be doing subtraction before addition. Okay, so let's try it out. Pause if you'd like to try these out, and then we'll go over the answers. Okay, 12 divided by 4 times 3. Okay, so no parentheses, no exponents. Then we have multiply and divide, and add and subtract. Okay, so from left to right, we'll do all the divisions and multiplications. So the correct answer here, do the division first. 12 divided by 4 is 3. And then 3 times 3 is 9. All right, next one. Parentheses first. 15 divided by 5 is 3. Okay, then do multiplication, 27, that's the 9 times 3, and then do subtraction. Okay, next one, parentheses first. So 5 times 8 minus 10 is negative 2. 2 cubed divided by 4. Okay. Then now I do have a parentheses here that I still wrote, but there's nothing to really do in there. That's used for clarification, just so you don't have a multiplication symbol next to a negative sign. So it's okay to move on to exponents even though you still see parentheses, because they're not indicating any sort of operations within those parentheses. The other thing to check, let's see, you want to make sure, if you have anything that like if you see a negative sign outside of the parentheses, all right, that's also not part of the parentheses, it's just indicating multiplication. So we'll do an example like that in a minute. But it's okay to go ahead in this one. We'll move on to exponents. Okay, 5 times negative 2. 2 cubed, 2 times 2 times 2, that's 8. And that's a divided by 4. Okay, then multiplication and division from left to right. So on the left we have 5 times negative 2, that's negative 10, plus, and then on the right, all right, we have 8 divided by 4, which is 2. And then negative 10 plus 2, negative 8. Okay, and then finally, this last problem uses curly braces. That's just another form of parentheses, so we usually start with the normal parentheses, then move on to brackets, and then if you need another one, sometimes you'll see these braces used. All right, so we want to do all of the parentheses, and within each parentheses we still follow order of operations, which means you would be doing parentheses first. So you just keep going until you find the very innermost set of parentheses, and that's where you start. All right, so this would be 84 divided by 4 minus braces 3 bracket 10 plus, and then here's the part we're doing. 15 minus 2 is 13. Okay, I don't need the parentheses anymore because I've finished everything inside. Okay, then move on, so we'll do the brackets next. Braces 3, 10 plus 13 is 23. And now I still do need some sort of I can do parentheses here or brackets, but I'm multiplying the 3 by the part inside the bracket. So I do need something that indicates multiplication. I can do parentheses or even just a multiplication symbol now. Okay, and times 23. Okay, and then do the curly braces. Okay, minus 3 times 23 is 69. Okay, then do division before subtraction. So that's 21. And then 21 minus 69 is negative, let's see, what's that, 48? Negative 48. Okay, and those are all of the examples. Okay, a couple notes on order of operations. First of all, watch out for things that are implied that aren't obvious or that might actually be the opposite of what you expected. So we already talked about implied parentheses. In this problem, you would do 4 plus 5 first, and then you would divide by 3. So if somebody didn't know what was happening, it almost looks like we're doing addition first before we do division, which is kind of the opposite of the order of operations. So it looks like it's incorrect unless you realize that there's a parentheses that's implied up here. So really we're doing parentheses and then division, and that's okay. That's the order of operations. The next thing I wanted to talk about was the correct use of the negative symbol. This actually means the opposite of. So when you see negative 3 squared, we sometimes do read it that way, but you could also read this as the opposite of 3 squared. Right? And the important thing on this one is that you need to know what's actually being squared. All right, so a couple ways to think of this. First of all, you can think of it as an exponent only applies to what's directly at its base. Okay? And we want to think of this little negative sign as kind of disconnected from the 3. So it's really, we're squaring the 3, that's 9, and then we're taking the opposite of that. So that's actually a negative 9. Okay, here the opposite of 3 squared means find 3 squared first, 9, then take its opposite. All right. You can also think of this as kind of a multiplication. If you see a negative sign, it really means negative 1 times whatever follows it. All right, so negative 5 is the same thing as negative 1 times 5. All right. Well, now when you see this, let me clear some of this out. Okay, so now when we see negative 1 times 3 squared, all right, by order of operations, we have 2 things to do, multiplication and an exponent. So you do the exponent first, and then you multiply to get negative 9. All right? Or if it helps you to think of it as a subtraction symbol, then think of it as there's nothing there in the beginning, so think of it as a 0 minus 3 squared. And then by order of operations, you would do exponents first, and then subtraction. Okay, so there's your exponent, and then subtract 0 minus 9 is negative 9. All right? Now, you might be protesting, maybe you're thinking, well, that should really be a positive 9. All right? Well, there is a way to indicate that. We would use a parentheses around the negative 3, and then put the squared outside. Now, that one is saying square the negative 3. This one means negative 3 times negative 3, which is positive 9. Okay, so without parentheses, that means apply a negative to the 3 times 3, which is negative 9. Okay? All right, let's try a couple more complex examples, and we will end here. Okay, so pause, try these out, and then I'll go over the answers. Okay, first problem. Start with parentheses. So there's an implied parentheses around the numerator and the denominator. So we need to work out everything on the top and the bottom of the fraction before we do anything else. Okay. On the top, we have more parentheses, so we'll start there. Okay, 8 minus 12. So 2 times negative 4 minus 11 times 4. Okay, and then in the denominator. Now you can kind of skip back and forth between these two problems. So we're working 2 at the same time. All right, so below the fraction line, there's nothing to do in the parentheses, so we move on. No exponents. Okay, then we move on to multiplication and division. So we do have multiplication. 5 times negative 2 is negative 10. Okay. In the numerator, we also have, we did all the parentheses. There are no exponents, so now we can also do multiplication. Okay, so 2 times negative 4 is negative 8. 11 times 4 is 44. And then in the denominator, we have, we can move ahead. We did all the multiplying. There's no dividing, so we can move on to subtraction. Right? Or you can think of this as negative 10 plus negative 3. Either one's fine. That's negative 13. Okay. In the numerator, we also have subtraction. Negative 8 minus 44 is negative 52. All right, and then finally we have a division. Negative 52 divided by negative 13 is positive 4. Okay, let's look at the next one. All right, we'll move over to the right. All right, 2 more implied parentheses, so we'll work out the entire numerator and denominator. All right, in the numerator we have multiplication. Negative 12 plus positive 10. Okay. In the denominator we have an exponent, 8. Okay, 2 cubed is 8. and then I'm left with addition and subtraction in both the numerator and denominator. All right, so in the numerator I have negative 12 plus 10 is negative 2, and in the denominator 8 minus 2 is 6, and 6 plus negative 6 is 0. Okay, negative 2 over 0. All right, what is that? All right, well, we're just going to say that that's undefined. Your calculator will give you an error. There are two reasons for this, and perhaps we'll talk about this later, but the issue with dividing by 0 is that sometimes there are no answers, no real answers, and then sometimes there are infinitely many real answers. Okay, in this case, there are no real answers. Okay, so this is undefined. This is not a real number. Undefined, not real. Okay, and then one final problem. All right, at the bottom here. Okay, so we have parentheses and we have brackets. These parentheses are just showing, just for clarification, they're around negative numbers, but there's no operations to do inside. So we can move on. We'll look at this bracket. And within the bracket, we have a choice of subtraction or this parentheses. So we'll start with the parentheses. Okay, so we copy everything else down. And then in the brackets, start with 3 minus 6. That's negative 3. Oops. Okay. Then moving on to the rest of the bracket, 4 minus negative 3. Now really this you can think of this as a subtraction, or if you want to even think of this as a multiplication, like a negative times a negative 3. Okay, so you could do that next. And that's going to become 4 plus 3. All right, 2 negatives makes a positive. All right, so 4 minus negative 3 is 7. All right, and then 2 more steps. We have a multiplication and a subtraction. So negative 8 times negative 3 is 24. 24 minus 7 is 17, I believe. 17. Okay. Alright, I think that's everything I wanted to go over. So to summarize, we talked about what is a math system, and we said that it's a set of symbols. So in this case, we're going to be using, for our symbols, all of the real numbers, and then we need at least one operation. So we talked about multiplication and addition. Okay? So you should now be able to classify real numbers, right? See what other subsets they're a part of, natural, integer, whole, etc., and then use the order of operations. Okay, that's everything. Thank you for watching, and I'll see you in the next video.